Hello, everyone. Thank you very much for tuning in to watch this video. My name is Dr. Andrew Brown. I'm from the School of Maths and Physics, and I'm here with my colleague, Professor Alan Fitzsimmons.
Hello there.
We're here to talk to you a little bit about maths and physics. And in particular, we're going to focus on one area of sort of maths and physics, which has a lot of overlap. It makes sense to have one topic for the talk. And the loose title we came up with was based around a particular experiment, which Alan will introduce later on, which is called the Young's double slit experiment, or Young's slits. And it has to do with interference, and interference in particular between waves of light. Now, as Alan will explain, whether light is a wave or something else is actually a bone of contention in physics historically. But in order for us to describe the phenomena mathematically, it's important for us to talk about waves. And so the images that we're seeing on screen at present, these are interference patterns caused by sources of waves interfering with each other. So you're familiar with waves in terms of water waves. This middle image here, it certainly sort of looks like water waves, but of course we have other types of waves. But mathematically speaking, all plane waves are described the same way, and you will be familiar with the idea of a sinusoid or a sine wave. And my animation has not worked for me there, so I'll go back for it. But a plane wave is just a sine, okay? So y equals sine of x is the kind of mathematical object that describes a wave, okay? So obviously we have cosine x as well, but hopefully you're familiar with the idea that a wave can be characterized by a number of different parameters. So a sine wave, for instance, has an amplitude that basically means the height from the x-axis that it gets to, and that actually corresponds as well to this circle image on the edge. So you might know that plane waves are connected to circular motion, and essentially as the arrow rotates around the circle, the y coordinate that is mapped out there is just the sine function that we're familiar with. So the amplitude is basically the size of the circle, or equivalently when it comes to the wave, the height above the x-axis that is reached by this blue line. And then the other aspect of plane waves that we're interested in is the frequency. The frequency has to do with either how rapidly this arrow sort of maps out the circle on the left-hand side, or equivalently it's related to the distance between successive peaks or troughs in our wave. Okay, so it's related to the wavelength. There is a third characteristic of plane waves, which is also very important when we talk about them and describe them mathematically, which is called the phase. That has to do with where on the circle you start, or where on the blue line you treat as being x equals 0. But it's not important for the purposes of this talk, so we're just going to focus on amplitude and frequency. Now, this is related to ideas that you can think of sort of intuitively. Frequency has to do with how many oscillations you have per unit time or per unit space, depending on what kind of wave you're describing. So the wave at the top here, the red one, has the lowest frequency. We have only a couple of oscillations in this sort of period of time. And the wavelength then is the distance between those peaks and troughs. So obviously the longer time between them, or the longer distance between them, that's a longer wavelength, that means a lower frequency. So these two things are inversely proportional. The purple or pink one at the bottom then has the highest frequency, so that's the most oscillations. Correspondingly then, it has the lowest wavelength. Now, so far I haven't shown you any maths as far as you might think. Anyway, I haven't shown you any equations, but we can think about plane waves and the relationship between the red curve and the purple curve here and all of the other curves as arising from the equation for the plane wave. So the general equation for a plane wave, and again, this is ignoring the phase, is just this equation. Okay, so the y, the sort of position along this y-axis, is governed by this relationship where you have some amplitude a and some frequency omega. So the amplitude then, this is like a stretch relative to the y-axis. So you'll be familiar with the idea of function transformation. So if you have some function and you multiply that function by a number, so that's all this amplitude is, you know that you will sort of stretch or squeeze that depending on whether the number is greater than or smaller than 1. So that sort of stretches our wave out in that direction. That gives us a different amplitude. The other number then, the frequency, the omega, this is a compression or a stretching relative to the along the x-axis in this example. Okay, so if I have f of x and I change that to f of 3x, what happens, sort of counterintuitively, I remember when I learned it, it seemed counterintuitive. If I put a large number in there, it actually squeezes the function up. So a plane wave, by increasing the frequency, I'm essentially squeezing the function and therefore having more oscillations as a function of time or of space, depending on what the actual value on our x-axis is. So those are the two quantities that are important. And what we're really interested in looking at in this talk is not just a single plane wave, but how plane waves interact with each other, and as we'll see, how they interfere with each other. So what that requires us to think about is what happens when we add together or combine several plane waves. So the first simple example is if we just take two plane waves of the same frequency. So that's a rather simple mathematical formula you see at the bottom here. So we're going to have one plane wave, which is just sine theta. So I'm treating the amplitude and the frequency as one here. And I add them together. So there's my first one and my second one. I add them together. You can sort of intuitively see that where I have the peaks and troughs will sort of combine to give me larger peaks and larger troughs. And that's what you can see on the right-hand side of my equation at the bottom there. I've just increased my amplitude to 2. So these two combine, and I end up with a plane wave of larger amplitude. That's what's called constructive interference. It's sort of skipped off the screen there. What happens then if we change the amplitude of the second wave? So what that really corresponds to is having one going up when the other goes down. So you can see my amplitude now has changed to a minus sign in the second sine wave. So sine theta plus minus sine theta, obviously you sort of know, will give 0. The two just cancel out. And this is what's known as destructive interference, okay? And this is actually how noise cancelling headphones work. So they will take the wave, or the waveform of the sound that's coming in, and they will flip it upside down and play that into your ears at the same time as the ambient noise is coming in. And the effect is to well, hopefully the effect is to cancel out the sound wave and give you effectively a 0 wave, which is silence, okay? So that's constructive and destructive interference. But what we've looked at is plane waves of the same frequency, okay? We've just had a sort of trivial frequency of 1 and amplitude of 1. What happens then if we combine waves of different frequencies? And this then is where the picture gets more interesting. So I can no longer just combine these into a single sinusoidal term on the right-hand side. It's not quite so straightforward to picture what's going on. So let's look at our two waves. Then let's say this green one at the top will be our sine 2 theta, because that's twice the frequency. And the red one underneath is our sine theta. It's the sort of fundamental frequency as we refer to it. What will happen when we add these two things together? Well, as we'll see, we can sort of break this up into little sections. So in the first section here, we can see that both the green and the red, I'm sort of assuming that both of these are oscillating about some 0 value. Both the green and red are positive. They're both going up in this region. And therefore, we would expect, just as we saw in the first interference slide, that these two things would add together and give us something constructive, okay? However, in the second part here, the green wave is down, it's negative, it's below the x-axis, while the red wave is up, okay? So these two then will cancel out and I'll get destructive interference. Now, you might assume that you get this green, red, green, red, green, red, or constructive, destructive, constructive, destructive the whole way along. It's a bit more complicated than that, because if you look at the next part, you'll actually see that once again, the two waves are at odds, okay? The green wave is positive while the red wave is negative. So I get another period or another section here of destructive interference. And then in the next one, that's when I get constructive again, because both are negative, okay? And so it continues. I get sort of constructive, constructive, destructive, destructive the whole way along, okay? So where these two things add together, then I expect that I will get a high amplitude. And where they interfere destructively, they cancel out, I will expect to get a low amplitude. And that's indeed what we see. This is the resulting wave. So you can see in the regions where I have constructive interference, I have this large amplitude, as in the green sections here. And in the periods where I have destructive interference, I get these sort of lower amplitude regions, okay? And you can imagine I could keep adding in more and more frequencies, and I would end up with more complicated waveforms. And I just want to show you something. This is a little applet. I'm going to come out of my presentation. This is a little applet for controlling this kind of summation. So here I have my sine x. If you look in the middle part here, so just in this region, it doesn't show up while I'm on it, but it'll show you the actual mathematical formula. So I've got an amplitude of 1 and a frequency of 1. That's just that fundamental that I was talking about. If I now bring in my amplitude of 1, frequency of 2, so that's the second harmonic, you see that's the yellow wave there. So the yellow one, there's the fundamental sine x. There's the second harmonic, as we call it, the sine 2x. When I add those together, I get this resultant that I just showed you on the slide. So a period of constructive interference followed by a period of destructive interference followed by constructive, destructive, and so on. Okay, and I can continue to add in more of these, and I can add them up in any amount that I want. I can sort of build up a recipe of plane waves. It gives me a more and more unusual looking shape in the end. And what's fascinating about this is that people have sort of worked out how to put together all of the various ingredients to build really any shape that you like. So any kind of function that I want to build in this on this lineup here, I can do that simply by combining plane waves of different frequencies. And obviously, I'm going to need lots and lots of different frequencies if I want to make interesting shapes. But for instance, I can build a sawtooth wave here. So this is something that looks sort of like a straight line and then jumps back down, straight line jumps back down. And you can see it's not quite right here at the ends, but more or less in between times, I get pretty much like a linear relationship, which is remarkable because sines and cosines are these nice curvy looking things. And yet when I combine them together, I can make them into something that looks like, excuse me, a straight line. Similarly, I can make like a square wave that looks like this, or the triangle wave. Okay, now the triangle wave, you can see it's jumped down to this line. Now is the cosines, because this is what we call an even function. And you can see that the fundamental looks sort of like a triangle, okay, but without the pointy bits at the end. So adding in these other ingredients, these other components, are what gives me the constructive and destructive interference necessary to build this, this triangle wave here. Okay, so this is an important idea in physics. It's also an important idea in engineering because this is used for a process known as synthesis. Okay, so if I go back down to 0, okay, so a sort of clear line here, what this tells me is that I can build up any shape I want simply by combining plane waves. And if I know what shape I want to produce, I just have to combine the ingredients in the right proportions, and I can synthesize or build a function, any function that I want. And this is actually the process that is used in the instrument called a synthesizer. Now, obviously, all the people watching this, if you're doing your A levels, you're probably too young to know what a synthesizer is, but it's an electronic instrument that was very popular in the 80s, used for producing very sort of strange sounding electronic music. And it worked on this principle of synthesizing plane waves together to form particular sounds. Okay, but you can also synthesize the sound of real acoustic instruments by adding together lots more frequencies and higher fidelity, and you can produce any sort kind of sound wave that you want. So that's one side of it. I can build any shape that I want. The other thing that we can do is go the opposite direction and start with some waveform that we have and analyze it in order to extract the component parts. So it's a little bit like being handed a smoothie and breaking it apart into its sort of constituent ingredients to work out how much of each ingredient is there. And that really corresponds to working out the amplitudes of each of the frequencies of the plane waves. Now, just to point out, if I go back to the slides here, this is my last slide, just to point out that this is actually a process that you're familiar with in a different context. If you're doing GCSE A-level maths, you would be familiar with the idea of resolving a vector into its components. Okay, so if you have a two-dimensional vector, sorry, I've got to go through these animations again. A two-dimensional vector like this green line here, you know that you can resolve that into its horizontal and vertical components, and that basically tells you how much of your vector is in the x direction, how much of your vector is in the y direction. We can do exactly the same thing with functions to work out how much of any particular function is in the sine x direction, if you think about it like that, the sine 2x direction, sine 3x direction, and so on. And we can work out what the components are, sum them, so we can synthesize a vector, we can break it apart into its constituent parts. We can do the same thing with a function. Okay, so that's all I want to say at this point about the sort of mathematical basis. So I'll hand over to Alan, which will require me to stop sharing my screen, and Alan can take over and tell you about the physics applications of these ideas. And I'll come back at the end to explain some more about some of these things. Over to you, Alan.
Great, thanks, Andrew. So we've heard from Andrew there, this mathematical idea of being able to add together different plane waves, different sine functions and cosine functions, and coming up with different kinds of shapes of waveforms through this principle of adding and subtracting, and constructive interference and destructive interference. Well, all of this is really important because of a long-held debate, as Andrew said at the start, in physics about what is light and what kind of thing is light, because by eye we can't see it travel. It travels too fast. We can manipulate it. We can reflect it off mirrors. We can bend it through glass or through water in refraction. But what is it? And over 300 years ago, it was a real hot topic of debate. And on one side, we had scientists like Isaac Newton, who was probably the most famous physicist in the world then, and is still pretty famous today. Through his laws of physics that he uncovered. And he was pretty sure it was a particle because light travels in straight lines. And we know that particles travel in straight lines if there's no force acting on them because of Newton's first law of motion. So surely light's a particle. Well, on the other side, there were a bunch of physicists led by Christian Huygens, a Dutch physicist. And he said, well, that's true, but there's evidence that light is a wave. And one thing he was able to do was show that if light is a wave, it explained refraction of light, the way that light bends when it travels through glass or water or any other medium than air. So there were arguments on both sides. But about 100 years later, in about the year 1801, a physicist and an optometrist called Thomas Young figured out he could actually work this out one way or the other. And this is what we call the double slit experiment. So he said, look, let's go and assume that light are particles. It's made of particles, little balls of something that are shooting around, and they go into your eyes and you see things. Well, what if, first of all, you have a huge stream of particles here on the left-hand side, and they hit a block through which there's two holes or two slits, then the only place where those particles can travel through will be those two slits. Some of them will travel all the way through, some of them might bounce a bit off the edges, but so then we'll have transformed our whole array of particles into two beams of particles, and then a little while later we'll let them hit a screen, and therefore we should see two bands of light corresponding to the two slits, where if particle goes through the upper slit, we see the light in that upper band. If a particle goes through the lower slit, it goes through the lower band. So that's what we'll see if we have light composed of particles. But he said, if light is composed of waves, then again we could send all these waves onto this first screen with the two slits in it. Then after those waves have passed through, they'll continue traveling to the second screen. And when they reach the second screen, depending on where you are on that screen, you'll either see the light arriving where one peak equals, it arrives at the same time as another peak, or trough, it arrives at the same time as the trough from the other slit. So you always have constructive interference. Or you'll have other areas where every time a wave arrives from the first slit that's got the peak like this, there's a trough from the second slit. So you get destructive interference. So if light is a wave, then on that second screen, you should get alternative bands of light and dark and light and dark. And so in 1801, he managed to do this experiment. It's pretty tricky back then. Lasers hadn't been invented. The only source of light that was constant was the sun. We didn't have real laboratories or accurate measurement equipment, but he managed to do this experiment, and what he saw were these bands of alternating light and dark. He had shown that light is a wave. So this is why Thomas Young's slit experiment, the double slit experiment, is so famous, or at least that was the first reason why it became so famous. Well, the good thing about this is that we can look at the mathematics of this experiment, and so we can measure the experiment that we actually do. So we can measure the distance between the slits over here on the left, and you can see that's A. We can measure the distance between the screen with the slits and the projection screen where we see these bands of light and dark, and that's the distance D. And then we can measure the distance on that screen between the light bands, and we can call that distance Y. And when we do that, we find there's a relationship between these measurements and the wavelength of light. And this is an equation that you may have seen already in your A-level physics. If not, you'll meet it later this year when you look at this experiment in some more detail. And what you see now is that the wavelength of light is given by a combination of the distance between the slits, the distance between the fringes, these patterns or these bright bands on the projection screen, and the distance between the two screens. And so we've changed this from an experiment showing the nature of light itself to an experiment that allows us to measure the wavelength of light. If we measure those numbers using an accurate ruler or some other device and put them into that equation, we can measure the wavelength of light. And this is what physicists often do. They take this mathematics, this fundamental mathematics, as Andrew was explaining, and transform it into something practical that can be used. And in fact, we can go even further, because now we understand this physics. We would call that experiment, the double slit experiment, an interferometer. Sorry, it's an experiment that uses the interference of two light beams. We can design another type of interferometer. Here, this is one called the Michelson interferometer, and where we take a single light beam on the left-hand side coming from a laser, split it up into two, and let it bounce off two mirrors before recombining, and then you get, again, this interference pattern you see on the right. And by the way, this is the kind of interferometer that you would be using in our first-year physics laboratories at Queen's. You'll be doing experiments with this, as well as looking at the nature of waves in ripple tanks. The important thing here is that where that interference pattern occurs, where those bands of light and dark occur in that interference pattern, depend crucially on the distances between the mirrors now. And so if one of those changes slightly, we'll see that interference pattern change. And so we can now use the wave nature of light to measure very small changes in distance, in fact, smaller than the wavelength of light itself by a great degree. That again is something you would be doing in first year physics labs here at Queen's. But I want to just show you this wonderful picture. This is one of the world's largest interferometers. It's the same principle. It's called the Laser Interferometer Gravitational Wave Observatory, or LIGO. There are 3 of these at the moment in the world, 2 in the United States, like this one in Italy, and the 4th one is currently just about to start operation in Japan. Down at the bottom center, you can see the laboratory from this aerial shot, where the beams are sent out and where all the scientists work. And then you have these arms going up to mirrors 4 kilometers away. And then the light is reflected off those mirrors and then back again. Not just once, they go up and down those 4-kilometer tunnels over 50 times. And when they then recombine in the laboratory, you get an interference pattern that is so sensitive, you can see the distance between those mirrors change by less than the size of a nucleus of an atom. And this is what allows these interferometers, we call LIGO, to measure distortions in the structure of space itself due to collisions between black holes in the distant universe. It's something that's only been possible over the past 5 years. And we now have, as I said, this array of observatories using these interferometers around the world, which study these explosions and these tremendous collisions between black holes throughout the universe. But let's go back to here on Earth, because we're satisfied light is a wave. But in 1905, 100 years after Thomas Young did his experiment, everything was thrown up in the air again, because we had experiments done which involved studying how when light is shone on a metal, you get a current. It's something called the photoelectric effect. And the problem with the photoelectric effect, again, something you will study in your A-level physics if you haven't done so already. The problem with this is that you cannot explain it using the wave nature of light. But instead, if you believe that light is a particle, and we call particles of light photons, and each photon has an energy given by a number we call Planck's constant times the frequency the particle would have if it was a wave, which is already sounding a bit strange, then you can explain the photoelectric effect. So it looks like we've gone back to square one after over 200 years of physical investigation. We didn't know if particles, or if light, was a wave or a particle. Thomas Young shows after over 100 years that, yet light is definitely a wave. Then just over 100 years later, Einstein shows that light is a particle called photons. Which is it? Well, we can go back to the double slit experiment, and we can say, well, here's the 2 choices. We've got the light passing through Young slits on the left-hand side and forming the interference pattern that we're familiar with. But what if on the right-hand side, the photons are coming through the slits? Maybe light is a particle then. But on the way to the slits, they're kind of bouncing off each other in a complicated fashion. And doing that, we end up with a pattern of light and dark on the screen, which impersonates what you get from constructive interference of waves. Well, now we can test that because we now have things like lasers and so on, and we can tune our experiment so that at any one time, if light is a particle, we're only sending one particle of light through that experiment at any one time. And if that's right, we should end up with just a couple of blobs of light on that screen because the particles are going through one at a time. There's no waves involved. So here's a recording of a screen where this experiment was done at the University of Leiden in the Netherlands. And we're starting at 25 milliseconds after the experiment. This is a very much slowed down recording of this experiment where they were sending through one photon of light, one particle of light at a time according to their calculation. Now, as we play the movie, you'll start seeing little faint dots of light, and that shows where individual particles of light, individual photons, were landing on the screen. And you can see, initially, it looks just pretty random. It looks like absolutely right. Light is a particle and not a wave. But as we let the experiment run, and we speed up the clock a little bit, we speed up the movie a little bit, you can start maybe seeing now that those particles aren't hitting randomly. Those particles of light aren't hitting it in two blobs. But as we watch it, we can see that there are alternate bands of light and dark. It looks like an interference pattern from waves. But this is crazy, right? Because remember, the photons are going through one at a time. How does a photon know where to land on where it's going to be light or not land, so it will be dark? It doesn't by itself. It's as if light was both a particle and a wave at the same time. And this is this concept we have in quantum physics of wave-particle duality. The fact that when we go down to the smallest things we find in nature, they're not a particle, it's not a wave, it's both at the same time, and something that's very hard to imagine. And this is one of the reasons, another reason why we believe the double slit experiment is one of the most fundamental, important experiments in physics, because it reveals this duality between waves and particles at the smallest levels of objects in our universe. But that's not the only thing that we get out of the wave nature of matter. For that, I'm going to hand back to Andrew.
Brilliant. Thanks, Alan. So I'll click screen share. I have to select that. Okay, so what we talked about earlier was this idea that light is this wave. I need to just exit for a second. Light is this wave. And what that means from a mathematical perspective is that this wave just goes on and on and on and on and on. Okay, a sine wave, as you know, has no start or end. It is defined across the entire real line. That's how mathematicians refer to it. What that means is for any value of theta that we put into this sine theta, between minus infinity and plus infinity, it doesn't matter. We put any value in there. This function, sine, has a value, and it has a well-defined value. So what that means is this oscillation goes on and on and on and on forever. Okay. Now, what that means is that the wave, if we're thinking about light as a wave, say, has a well-defined frequency. Okay, we just measure the distance between these two peaks, and we can do that using the Young slit experiment, as Alan explained, and we can work out what the frequency is. But where is the light? Okay, that's, you know, sort of saying like where is the particle of light? Where is the photon? You know, we can't say that it's just at the middle there, because there's no difference fundamentally between that peak and the peak next door to it, or over here, or anything else like that. There's no idea, we have no idea really where that wave is. Is it localized to some region of space? And in fact, it's not localized at all. It's what we say completely delocalized. On the flip side, then, we can have another type of function. So what that tells us is we know the frequency, we don't know the location. Okay. On the flip side, we could have another type of function. This is a function called a Dirac delta function. And this function is zero everywhere, except for just at this little, at one point in the middle there, where it's equal to 1. Now, for this function, we know exactly where the function is, if you like, or where the particle is if we're using it to describe a particle. But what's the frequency? Okay, Well, there is no frequency because this isn't a periodic function. It doesn't rise and fall and happen repeatedly over the real line. And therefore, we have no idea what the frequency is. Now, what we showed earlier on with the sort of Fourier synthesis for analysis kind of idea, that's where we were adding together all the plane waves, is that we can construct any kind of shape that we want. And actually, we can construct a shape that looks like this blue line simply by adding together lots and lots and lots of red lines, okay? So we're targeting something that looks like the blue line. And as we add together lots and lots of plane waves, we can make something that looks like this line below, okay? Now, that doesn't look much like the line above, but what we find is that as we add in more frequencies, we keep adding more and more and more. This gets narrower and narrower and narrower until in the limit that we have infinitely many frequencies, i.e. we've added together infinitely many plane waves, it actually turns into this Dirac delta function. It's just this one point, which is non-zero. Now, this seems like a sort of weird mathematical idea, weird sort of mathematical trick. The idea that we could have infinitely many plane waves, which are delocalized, they go on and on forever. But when we add them together, there is destructive interference everywhere except for at a single point. And the sort of flip side of that is that if we want then to understand the sort of behavior of the physics that this describes, okay, we can relate it back to what Alan was talking about earlier about the photoelectric effect. The energy of a photon, in fact, the energy of any given particle or quantum particle, is related to its frequency, the frequency being that of the wave. Okay, so if we're thinking about a particle of light and we want to say, oh, the particle of light is here at this point, well, what that means is we need infinitely many frequencies, infinitely many energies in order to say that with any certainty. And this is what's known in physics as the uncertainty principle. And the idea basically is if you know exactly where a particle is, you actually know nothing about its energy. Actually, more accurately stated, if you know the position of a particle, you know nothing about its velocity or its momentum. So if I measure a particle and say, oh, yes, it's definitely here, then what that means is it could be moving in any direction. We have no idea. Conversely, if we know exactly how fast it's moving and in which direction, i.e. we know its velocity with exact certainty, we have no idea about where the particle is. It's completely delocalized. And that seems hard. Well, it is hard to get your head around, I confess. It's not easy to explain in a quick presentation either. But when I first heard this, what I thought was that this was an experimental problem. Experimentalists try to measure quantum things, and basically our instruments aren't good enough. Maybe even the human eye isn't good enough, or the human brain isn't powerful enough to comprehend these things. But in actual fact, actually there in the mathematics that underpins all of this, it's shown that this isn't just some artifact of a badly done experiment or some limitations of our technology. This is actually a fundamental characteristic of the universe we live in. It's a fundamental characteristic of quantum mechanics that we have this inherent uncertainty about measurements that we make. And that's really fascinating. Now, perhaps you're not interested in quantum mechanics at all, but actually this principle is immensely important as well for everyday life. In fact, the communication system, which is transporting this video to you now, which is probably an optically based communication system, i.e. sending information through the internet, is based on a similar kind of principle to this uncertainty principle. The idea is that to encode information in light, what we do is we attach bits of information to each frequency in the light. And the more frequencies we have at our disposal, then the more information we can pack in. But what this principle tells us is the more frequencies we pack in, the shorter the pulse of light becomes. It's very counterintuitive. You would think that adding more frequencies in, you would make this big bulky thing, but in actual fact, it works the other way around. And that's because the more frequencies you add in, the more destructive interference we get, squeezing our pulse into an ever shorter period of time. And so the idea of bandwidth, when it comes to broadband internet, is this idea that we have a broad range of frequencies, but that actually necessitates having very short pulses of light to send the information. So that's everything I wanted to say about the uncertainty principle, and I'll hand back to Alan just to finish off the talk.
Well, thanks, Andrew. So the important thing is that hopefully we've demonstrated to you using this discussion about waves and the dual slit experiment, how mathematics and physics working together really underpins our understanding of our universe, how it works, and at least to our knowledge at the moment. And because of this joining between these two disciplines, of course, we offer degrees, what we call joint degrees in the School of Mathematics and Physics, that are roughly 50% mathematics, 50% physics, with the great interplay between them. So first of all, we offer degrees in applied mathematics and physics, which a lot of it would concentrate on these quantum ideas and how we take the mathematics and apply them to what we observe in the universe. We also have our theoretical physics degrees, which perhaps concentrate more on the mathematical underpinnings that we use in physics and how we make sure they're rigorous and how we make sure they're self-consistent. But the important thing is that if you apply to either of these degrees, choosing between them is not a problem, because students in both of these degree pathways do exactly the same courses in first year. And because of that, you can choose one of these degrees to embark on. But if you, say, towards the end of your first year with us, decide you're possibly more interested in the physics side, then we'd push you towards perhaps going or enrolling on the applied mathematics and physics pathway at that point. If you, however, are really excited and curious about the mathematical underpinnings and where that leads us in terms of understanding our universe, then we'd point you towards the theoretical physics degree. But it's a decision you don't need to have made when you first arrive with us. It's not set in stone. So I hope we've encouraged you to consider these degrees. I hope we've demonstrated some of the fascinating science that we can uncover with you when you embark on these studies, and hopefully we'll see you in our lectures sometime soon. Okay, bye.
Bye-bye.